Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Mikhail Beznogov with us today. Hello, Mikhail.
Hello, Frank.
Well, thank you very much for agreeing to talk about your very lovely article. Appreciate it.
Yeah, thank you.
And Mikhail, what is your geolocation? Where are we taking this call today to? Where are you at?
Well, I'm currently at home in Magureli. This is a small town near Bucharest.
Bucharest, Romania. Awesome. We are halfway around the world. So
yes.
And it is February 20th of 2023 as we record this. And I'm in Phoenix, and spring is coming. Spring is coming in Phoenix. How about in Romania? Are you starting to warm up, or we still got snow?
Yes. But basically, last week it started to turn from winter to spring.
Cool.
The snow has melted already.
Equinox is coming. Woohoo! All right. Very cool. And Mikhail, what do you like to do for research?
Well, I'm studying neutron stars, mostly their thermal evolution. Now I'm also more focusing on the equations of state of the neutron star matter.
Ooh, that's a lovely topic. Awesome. Very good. And that is going to bring us to this very awesome APJ article. It's open access, people. You can go get a copy for free. Go grab one. Standard cooling of rapidly rotating isolated neutron stars in 2D. And Mikhail, take us away.
So yes, that paper is devoted to cooling of rapidly rotating neutron stars. The work was done in collaboration with Jérôme Novak from Paris Observatory in France, with Denis Page from Institute of Astronomy at the National University of Mexico, and with my current collaborator Adriana Raduta, who works in the National Institute for Nuclear Physics here in Romania.
Cool. Very nice. Yes.
Okay, neutron stars.
Okay, neutron stars.
Neutron stars usually born in supernova explosions or in collapse of white dwarfs, and they start their life as proto-neutron stars. Some alternative scenario is that neutron star can be reborn in a merger of a binary neutron star system, but only provided that it survives the event. That is, it doesn't collapse to a black hole.
Right. Okay.
Neutron stars are the most dense and the most intriguing objects in the universe. They provide a unique opportunity to study the properties of cold superdense matter, and the equation of state of that matter is the most wanted characteristic.
Indeed.
Now, the mystery of the equation of state involves two facets: its pressure versus density dependence and chemical composition. Now, pressure versus density dependence is in some sense easier. It can be inferred by different techniques, for example, independent measurements of masses and radii. That's what nicer people are doing.
Okay.
And gravitational wave observation of binary neutron star mergers.
Right.
The question of composition is much more trickier. And neutron star's thermal evolution is one of the most promising ways to answer that question.
Okay.
To investigate thermal evolution, we need to solve, in general case, two types of equations: mechanical structure equations and thermal balance equations.
Yes.
However, in particular case of long-term cooling of neutron stars, the situation gets significantly simplified. A few hours after the birth of the neutron star, its temperature drops below 10 to the 10 Kelvin. And taking into account that neutron stars are very dense, this temperature is low enough for the matter to be considered at zero temperature. And this allows us to decouple mechanical structure from thermal evolution equation.
Okay. Yes.
Okay, so the main driving source of neutron star cooling is neutrino emission and at the later stages photon cooling. Among the neutrino emission, there is a standard so-called slow cooling by modified Urca process and Bremsstrahlung, and there is a possibility of some faster neutrino processes like direct Urca or Cooper pair break-in formation if we take into account superfluidity of neutron star matter.
Yes.
However, whether Durka processes or any other faster cooling processes occurs or not depends on the equation of state of the neutron star matter and on the superfluid gaps.
Yes.
So neutron star cooling is being investigated already for, I don't know, 45, 50 years. But mostly in spherical symmetry in one dimension.
Yes.
To go to even two dimensions is tricky because it requires to recast the equations of thermal evolution, as they have to take into account general relativity effects.
Space-time is moving. Yep.
Yeah. So I guess we can skip the literature part.
Okay.
Okay. So here we will in this paper we present our first result obtained with our new cooling code NS-Cool2D rod, which is a major upgrade of one-dimensional NS-Cool, a code developed by one of our co-authors, Denny Pash. And the code that is widely used for a variety of neutron star thermal evolution calculations, like long-term cooling of isolated neutron stars, cooling of neo-neutron stars, heating and cooling of accreting stars in low-mass X-ray binaries, and so on.
Yes.
And here we present its first extension to 2 dimensions.
Very cool. Very cool.
Now let's switch to equations for thermal evolution of rotating stars.
Okay.
Calculation of space-time metric and structure for axisymmetric rigidly rotating neutron stars in full general relativity is a complicated issue. Relatively simple procedures exist only in the slow rotation approximation. However, it is not very applicable for fast rotating neutron stars, and we want to focus specifically on fast rotating neutron stars. So we need to solve the full coupled system of mechanical structure and Einstein field equations. And one of the most efficient and accurate methods was proposed in 1993 by Bonassola and co-authors. And the numerical integration is based on a spectral method. So in this work, we employ Larine library suitable to deal with rotation frequencies from 0 up to the mass shedding limit.
Yes.
Important assumptions about the motion of the matter are the following. The motion is assumed to be axisymmetric, of course, with respect to rotational axis, stationary, purely azimuthal, no convection, no meridial incurrence, and what is important, we also neglect mass flows that might be induced by heat transfer.
Okay.
And last but also important assumption is that equation of state of the matter is barotropic, that is, it doesn't depend on temperature.
Cold. Good.
Yes, so following the notation introduced in the papers of Bonassola and other papers related to Larine, we can write down the components of the metric tensor, choosing the natural tetrad, and the equation 1 represents the components of the metric tensor, and there NA P, and N phi are four metric functions that depend on R and theta, but not on T and phi.
Okay.
Here, these four metric functions has to be computed together with the mechanical structure of the rotating neutron star.
Mm-hmm.
At this point, I want to emphasize that unlike spherically symmetric case, we have now four independent metric functions, and a Schwarzschild metric only has two independent functions.
Good.
So the number of metric functions has doubled.
Mm-hmm.
Okay, and then we can write the standard expression for the line element. It is written in the equation 2.
Yeah. Mm-hmm.
And the next topic is heat transport equations. So energy balance and energy transport equations were first derived by Miralles in 1993 from a general relativistic Boltzmann equation, and they can be written as it is written down here in equation 3. Here, CV is heat capacity, Q stands for heat sources or sinks, and in our case, it's only heat sinks because we do not consider any heating. We consider only cooling by neutrino emission.
Right. Okay.
Also, what is important to emphasize here that H tilde with subscript in brackets is a heat flux, but it's not actually a vector. This object does not transform as a vector. However, HE with a superscript is a local heat flux, and it is a vector.
Yes. Okay. All right.
This will be important later in writing boundary conditions. Here, omega is rotational frequency, and I guess other quantities are rather straightforward. All redshifted quantities are denoted with tilde, local quantities without tilde. So equation 7 explains how we redshift the temperature for rotating case.
Yes.
Okay, so if we move
with you.
further.
I'm with you. And 7, let's go over to 8. All right, there we go. Oh, there we go. Okay, those are the energy fluxes. Okay.
Yeah. So the energy fluxes are calculated in the diffusion approximation, that is, they are proportional to the gradients of temperature. And here, for simplicity, we assume the thermal conductivity kappa is scalar.
Okay.
Then we can recast this system of equations into one second order partial differential equation for redshifted temperature. This is the equation 10. Cool. And write it in its final form as presented in equation 11. Here I want to point out that equation 11 has the form of a classical heat diffusion equation.
Yeah.
It is parabolic and allows for instantaneous heat propagation. And so one might question the validity of such an equation in the framework of general relativity. However, this issue was previously addressed, for example, by Domes and co-authors, and those authors demonstrated that instantaneous propagation of heat is compatible with jar as long as the hydrodynamic description is applicable. And we are interested in long-term thermal evolution with time scales of hundreds and thousands of years, and hydrodynamic time scales are milliseconds for neutron stars. So we are very safe in using this equation.
Yeah. All right.
Okay, and like every partial differential equation, we need initial and boundary conditions.
We do.
So the initial condition is chosen rather straightforward. We introduce some small temperature gradient from the star center to its surface, and the temperature is assumed to scale logarithmically with density. This setup corresponds roughly to constant internal heat flux and makes boundary and initial conditions more compatible. For example, for neo-Neutron stars, we need to have a dedicated matching procedure to make initial and boundary conditions fully compatible. But for long-term cooling, there is no need to be absolutely precise in matching the initial and boundary conditions.
Okay.
So now boundary conditions. At the origin and on the symmetry axis, they're straightforward. They consist in requiring that temperature is regular and axisymmetric. There is nothing more complicated
Right.
than that. However, the surface boundary condition is different. Following the standard approach in studies of long-term neutron stars, long-term evolution of neutron stars, we split the neutron star into the star itself and heat blanketing envelope.
Okay.
The main motivation to do that is that while most of the star is very dense, degenerate, and its structure does not depend on temperature, the very outer layers of the star, they're not dense enough to be considered at zero temperature.
Yes.
The equation of state of the outer envelope depend on temperature.
Indeed.
And so we split it and compute the envelope separately.
Okay.
And from the envelope computation, we can obtain the relation between temperature at the top of the envelope, which is the surface of the star, with the temperature on the bottom of the envelope,
Yes.
which is the surface of the main cooling calculation. And that calculational surface is related to actual surface via the heat blanketing envelope solution, which is usually called TSTB relation.
Okay.
The typical density of the bottom of the envelope is 10 to the 10 grams per cubic centimeter. Such density is needed that at densities higher than this density, we can consider the matter to be at zero temperature.
Yeah. Okay.
So we need to formulate the boundary condition that will link computational surface with actual surface.
Good.
It is rather simple in principle. The normal projection of the heat flux vector at the bottom of the envelope is the surface flux. So we then write down the heat flux. Yes, equations 14 and 15, and we take it at the bottom of the envelope. Then we define the normal to the surface.
Right.
And yes, here in 16 and 17.
Yes.
Here, capital R defines the radial coordinate of the computational surface. And then we compute the projection of the heat flux onto the normal taken at the outer boundary of the star. So on one hand, this flux is given by equation 18. On the other hand, it is given via TSTB relation. Equation 19, I guess.
Yes, let's get over that one. 19, there we go. Sure.
Yes. On the other hand, it is given by TSTB relation. And combining these two equations, we are getting our surface boundary condition. Okay, so I guess we can move now to the models of rotating stars.
Okay, very good. I'm with you. I'm with you.
Yes. So to investigate the dependence on the equation of state, we computed thermal evolution for three different core equations of state and two different crust equations of state. Some properties of these equations of state are listed in table 1. So they provide some properties of the nuclear matter, computed with these equations of state, and some astrophysical properties like maximum mass of a neutron star is given equation of state, radius of 1.4, solar mass star, combined tidal deformability of the famous GV 1708-17 event, and also the density and the corresponding mass of the threshold of the direct Urca process.
Okay. All right.
Yes, so we tried APR, EUF, and then L3 omega rho as equations of state for the core.
Yes. Okay.
Okay. For the crust, we use a combination of Hansel, Zhdunik, Drobachevsky, supplemented by Nageli-Voterin equation of state, and also one of the much more new, much more modern. They're not listed in the table.
Mm-hmm. Yes.
And also much more modern D1M class equations of state for the crust.
Okay.
If you go further.
Yeah. Oh, there we go. Sorry. Table 2. Here we go. All right. Good.
Okay. Yes, and so this D1M class of equations of state for the crust. These two different equations of state for the crust, they provide almost identical pressure versus density dependence, but significantly different chemical composition of the inner crust.
Yes.
But I will return to this question a little bit later.
Okay.
Core and crust equations of state are matched smoothly at half of saturation density. And here it is important to note that Laurine, the code we use to compute the mechanical structure, is a spectral code, so it's rather sensitive to the smoothness of equations of state, and we have to do a slight smoothing to make it smooth enough for Laurine to work.
Okay. Yep.
So before studying thermal evolution, let's quickly look at the mechanical structure.
Okay.
So we have studied the neutron stars. Okay, first of all, we choose to compare neutron stars with equal baryonic mass, because baryonic mass is a conserved quantity when the star spins down or spins up, if we disregard accretion and mass loss.
Okay.
In principle, stars with equal gravitational mass can be compared, or stars with equal central density can be compared, but we consider that the best choice is to compare equal periodic mass stars.
Yeah.
So we have chosen 1.6 solar mass value of a baryonic mass, because gravitational mass corresponding to this baryonic mass is around 1.4, which is a canonical mass of a neutron star.
Yes. Okay.
So we have considered non-rotating star, and then two frequencies, 716 Hertz, which corresponds to the fastest spinning millisecond pulsar known to date, and then 99% of the Kepler frequency, and this frequency is equation of state dependent.
Yes.
So in table 2, some properties of these stars of the considered models are listed. So for each core equation of state, we considered 3 frequencies: static star, 716 Hertz,
Okay.
and 99% of Kepler, which depends on the equation of state.
Right. Good. Okay. I'm with you.
Yeah, okay. So here we can see that gravitational masses are very close, despite different equations of state and rotating frequencies.
Mm-hmm.
The radii, of course, they depend on both equation of state and rotational frequency. The same goes for the crust thicknesses.
Yes.
However, what is interesting, for example, if you look at column zeta, that stands for the polar to equatorial axis ratio. Yes, this column.
Ratio. Mm-hmm.
That all stars rotating at near Kepler frequency has very close axis ratio, despite different equations of state and despite different frequencies. The axis ratio of near Kepler stars are very similar.
Yeah. Okay. Yeah. Yes. I'm with you. Mm-hmm.
Here also, it is worth mentioning that the values of radii provided in this table might surprise a lot of researchers, but the trick is that they are written in quasi-isotropic gauge that is used by Lorin and in our thermal evolution equations. And this gauge is different from standard Schwarzschild gauge, and so the values of radial coordinates are different.
Okay.
And it is important to notice that for rotating stars, it is impossible to transform quasi-isotropic gauge into Schwarzschild gauge.
Okay, sure.
Okay, so I guess we can look at figure 1 that shows the mechanical structure explicitly.
Okay. Ooh, very nice figure. Okay.
Yes, so this figure shows the mechanical structure of rotating stars with APR equation of state. Left panel corresponds to 716 Hertz, right panel corresponds to near Kepler frequency.
Ooh, nice. Okay.
So the contour lines are marked with logarithm of density.
Okay.
The black ones are in the core. The magenta one is a crust core boundary, and the blue one is the computational surface. That is the bottom of the heat blanketing envelope. And the yellow band emphasizes the crust. So we can see that even 716 Hertz is not enough to strongly deform the star. We can see that the deviations are not really big. However, at near Kepler limit, the situation changes, and especially the crust of the equatorial region gets noticeably deformed. Can see that. Okay, and we can switch to figure 2. That figure shows radial profiles of density for different rotation frequencies and different lines of sight for polar and equatorial lines of sight and different rotation frequencies.
Right. Okay.
Here we see that as the star spins up, the central density drops, which is completely logical because the star expands, so the density in the center drops. Okay, I guess this figure is just illustrated. We can move further.
Cool. Good to get the basics down there.
Okay, and probably the last thing I want to mention before going to actual thermal evolution is the choice of frequencies and spin down. So we consider constant frequency, so we disregard any spin down, for example, due to magnetic braking. This is reasonable simplification because for isolated neutron stars, the magnetic fields are not necessarily strong. They might be strong, they might not. So this is reasonable. And the second comment regards the choice of near Kepler frequency. Stars rotating at near any small perturbation. No, it's not actually here. Stars rotating at near Kepler frequency, any small perturbation will cause a rapid loss of angular momentum due to gravitational waves emission. For example, this might be caused by R mode instability, F mode instability, thermal or magnetic mountains. The theoretical computations and the fact that we do not know any pulsar rotating faster than 716 Hertz both demonstrate that this mechanism of losing angular momentum is extremely efficient. So we do not expect any neutron star to be able to maintain near Kepler frequency long term. And so studying long-term cooling of that stars is academic. We do not expect to find any such star. However, we still consider this case as a
limiting
opposite limit to non-rotating star to see the maximum possible extent of effects caused by rotation.
I'm with you. Yep.
And I guess now we can switch to thermal evolution explicitly.
Okay, thank you for that. Okay, thermal.
Yes, so if we focus on figure 3, this corresponds to non-rotating stars, so spherically symmetric stars.
Okay.
Left plot shows the bottom temperature, right plot shows the surface temperature, and for 3 different equations of state. So to familiarize, mentioned here, to familiarize ourselves with this typical cooling curves, there are some vertical lines that denote changes in different cooling regimes.
Yes.
So the first regime is usually referred to as a relaxation from initial conditions.
Okay.
The second phase is early plateau phase. Third phase is crust core thermalization. Fourth phase is neutrino cooling, and the last phase is photon cooling.
Okay. Okay.
We can see that the bottom temperature is very similar for all equations of state up to the crust core thermalization stage.
Right here. Yes.
This is logical because we start with identical initial conditions. The equations of state of the crust are the same. So while the cooling is dominated by the crust, it follows exactly the same route. And the difference at the crust core thermalization is can be explained by the difference in geometry. Different core equations of state provide stars with different crust thickness.
Got it. Okay.
The core is cooling faster than the crust due to more intensive neutrino emission. So a cold wave is formed in the core and goes through the crust.
Yes.
And the thicker the crust is, the longer it takes for the cold waves to go through the core. And if we see here, APR cools faster and NL3 omega rho cools slowest in the stage 3. If we go back to table 2, we will see that APR has the thinnest crust. Yes, we see that for non-rotating star, APR has the thinnest crust, 0.82 kilometers, and NL3 omega rho has thickest crust, 1.39 kilometers.
Right. Okay. Good.
And so we clearly see this in the cooling figure that the star with thinner crust starts to thermalize quicker than the star with thicker crust.
Makes sense.
The figure on the right shows the importance of TS-TB relation. We can compare early plateau phase. Bottom temperature is identical and surface temperature is different. This is due to the fact that surface gravity acceleration enters TS-TB relation. And again, stars with different core equations of state have different surface gravity accelerations. And so the surface temperature is different even with the same bottom temperature.
Yes.
But all this was known because this is non-rotating stars. So let's move to next figure for rotating stars.
Okay, rotating. Let's see how we change. And oh goodness, lots of change. Okay, let's do the bottom.
So now it's the same, but for rotating stars with APR equation of state.
Okay.
So we have polar temperature with solid lines, equatorial temperature with dashed lines, and we also have non-rotating star for reference. It is a solid blue curve.
Right. Okay. Very good. I'm with you.
So we can see that polar temperatures are not affected by rotation, which is not very surprising because the star is not very deformed in polar direction. And the temperature gradient is mostly radial there, as we will see in the next figure. However, in the equatorial direction, we see some change, especially for the fast rotating star. We can see that its early plateau phase is shifted and the crust core thermalization phase happens later.
Yes.
Is also relatively easy to understand because we saw already on one of the previous figures that the crust in the equatorial region becomes noticeably deformed, and it becomes thicker.
Figure 1.
So the cold wave that originates at the core takes much more time to cross the crust in equatorial direction compared to the polar direction. And so we see that the polar curve diverges from equator. Yes, here.
Much fatter there than it is there. Yep.
Yes. Yes.
Very good.
A
Cool.
purely geometric effect.
Yes. Okay.
Yeah. Okay, and so the equatorial curves start to diverge from the polar one. And figure on the right again shows the dependence.
Ooh, very different.
Shows the big impact of the surface gravity acceleration on the TSTB relation. So again, we can see that bottom temperatures are different, but to much less extent. And surface temperatures are much more different because, again, surface gravity acceleration enters into TSTB relation. Yeah. And here we can see that, of course, for faster rotating star, the surface gravity acceleration on equator is considerably less than on the pole. Yes. And we can see that the green dashed curve is much more shifted than the green dashed curve on the left panel, where we consider bottom temperature.
Right.
Yeah. Okay, so let's move to the next figure. I guess it's figure 5.
Cool. Very nice. Very nice.
Yes.
Ooh, colorful one. Okay.
Yes.
Let's do a global. Let's do a global, and we'll zoom in if we need to.
That one. So this figure shows the temperature distribution inside the star for 3 different ages: 10 years on the top, 150 years in the middle, and 300 years in the bottom.
Okay.
On the left is 716 Hertz, and on the right is near Kepler frequency, and both have APR equation of state.
Nice.
Okay. You can notice that the stars become spherical. That is because the radial coordinate here is not actually radius, but logarithm of density. And in such coordinates, the deformation of the star is not observed. It is hidden in the radial coordinate.
Okay.
Also, this figure emphasizes the crust, because the crust goes basically from 10 to 14, and the core is just very small part in the middle.
Right.
Yes.
Right.
So we can see that at 10 years, the temperature gradient is mostly radial. There are some small deviations only at the equator, in the equatorial plane, but they are not that much.
Not huge, yeah.
At 150 years, the situation gets completely different. Yeah. We can see that, yes, we can see that at higher densities, more than 10 to 13, and in the core, the gradient of temperature is still mostly radial. However, in the outer parts of the crust, from 10 to 13 in logarithmic scale, we can see that the situation is completely different. A heat blob forms in the crust in the equatorial plane, and this heat blob acts almost as a point source of heat that flows in all directions from it.
Okay.
And we can see that for faster rotating star, the configuration of the heat blob is even more complex.
Even bigger, right? Right.
Yes, it provides higher temperature gradient, and it has less spherical shape, so to say.
Very interesting.
And at 300 years, qualitatively, the situation is the same. We can still see the heat blob. But if you look attentively on the temperature scale, you will see the difference.
Yeah.
For slower rotating star, the temperature scale goes just in a very narrow domain. Basically, it means that the star has already thermalized.
Oh, yeah. Okay.
So that star at 300 years is already entering neutrino cooling stage, and it has already thermalized. But for faster rotating star, the situation is different. There is still some noticeable temperature gradient provided by the heat block. So the star has not yet fully thermalized.
Okay, cool.
So as we already seen on the previous figure, the fast rotation postpones thermalization.
Yes.
By a few hundred years.
Mm-hmm.
Despite its complicated shape, the main idea behind the heat block is quite easy. During the crust-dominated cooling phases that starts from the birth till few hundred years, the crust, the cooling of the crust is driven both by heat conduction and neutrino emission. Rotation makes the crust thicker in the equatorial regions.
Back to that. Yeah. Okay.
The volume is increasing. The volume is increasing, and so does the total heat capacity of this part of the crust, and total neutrino emissivity of this part of the crust. However, the heat conduction is proportional to the surface area of the interfaces between equatorial regions and the rest of the star. And these interfaces, the area increase of the interface is less than the volume increase of the equatorial region.
Okay.
So the heat conduction becomes limited. The heat conduction becomes limited, and the equatorial region becomes a reservoir of heat because it can store more heat, but it cannot transfer it fast enough.
Okay.
And that is the main idea behind the heat block.
Thank you. That was very nice.
Yeah, so I guess we can move further.
Okay. Let's do figure 6.
Yeah, so this is just a radial cross-section for 150 years, so for the middle panel of the previous figure. And it also shows the difference in radial coordinate. So on the left, we plot temperature as a function of radial coordinate, and on the right, the temperature as a function of logarithm of density.
Yeah.
And we can see how it visually changes the same curves. On the right, the core is just from a dotted line to 15 on the right.
Okay.
And everything else is the crust. And on the left, the core is from 0 to at least 8 kilometers, and the crust is just a small part.
Yes. Okay. All right.
So from here, we can see that first, the core is already isothermal. There is no radial gradient, and polar and equatorial temperatures are exactly the same.
Yep.
Crust is noticeably not isothermal. Polar temperatures that are shown in solid lines, they almost do not depend on rotation frequency, but equatorial temperatures that are shown in dashed lines, they show significant dependence on the rotation frequency.
Get that hot pop in the middle. Yep.
Yeah, and we can see here how this heat block looks in its cross section, so to say.
It's an official term, blob.
Yes, of course.
Highly
okay, so we can also now look for angular distribution of the temperature, because it's also rather funny. Next figure.
Oh, yes. Okay, sorry. There we go. Here we get some data's going.
Yes, yes, this figure. So this shows the normalized temperature, normalized by its value on the North Pole, as a function of the polar angle for different moments in time for 716 and near Kepler frequency.
I see.
Yeah, so we can see that in both cases, early on, the temperature on equator is less than the temperature on the pole. And at later time, it inverts. The temperature on equator becomes higher than the temperature on the pole. And in the intermediate phases, we can see that the maximum is reached at some intermediate angle.
Okay.
And we can and by vertical scale, we can also see how the amplitude of this change depends on the frequency. Yes. Here it's just a few percent, and on the right, it's 20–40%.
Right. Oh, yes, much bigger breakup. Yes.
Yeah.
Okay.
Okay, and probably the most interesting plots are the next one.
All right.
Yes. So this plot shows the ratio of polar to equatorial temperature at the bottom of the envelope on the left and on the surface on the right.
Yes.
For different rotation frequencies and different equations of state as indicated by the legend.
Okay.
So we can see that this
Mm-hmm.
that at early time and at late time, this ratio is equal to 1. At early time, because we start with identical initial conditions,
Yes.
and at late time, because the star becomes isothermal.
Thermal. Yes.
In the intermediate times, the behavior is quite complex. We can see 3 extrema. The last minimum is due to the cold wave propagation that I already discussed.
Okay. Mm-hmm.
Yes, because the cold wave first reaches the pole and then the equator, because the crust at the pole is thinner than at the equator.
Uh-huh.
And we can see that the ratio drops below 1 because pole becomes colder than equator first.
Yes. Right.
Here we can see that at 716 Hertz and at near Kepler frequency, the ordering in amplitude is inverted. We can see that through, yes, the ordering in amplitude is inverted. And actually, this ordering in amplitude is proportional to the crust thickness ratio. That is the trick, not to the full axis ratio, that is the ratio of the radius on equator to the radius on the pole, but to the ratio of thicknesses of the crust in polar and equatorial directions.
Yeah, big one. Mm-hmm. Cool.
Yeah.
Very nice.
And on the right, we can see the effect again of the surface gravity acceleration. The dotted lines of corresponding color is the ratio of surface gravity acceleration on the pole to the equator to the power 1/4. That is how TSTB relation scales, and we can see that each curve starts on the corresponding line and ends on it.
Got it. Okay. Now here we go.
So yes, we have 6 models here, 3 equations of state, 2 frequencies. So each model has different ratio of surface gravity acceleration. Yes. So each of them starts and ends on the same curve.
Yes. Yes.
Okay, and
boink, boink, boink. Yep.
Yes.
Yeah, sort the same. They always thermal. Okay, I'm with you. Cool.
So we can move to figure 9.
Figure 9. I think that's the last figure. In figure 9, polar to equatorial.
Yes, it shows the same as the previous figure, the ratio of polar to equatorial temperature as a function of time, but at different densities inside the star.
Yes.
So curve labeled 10 is what we saw on the previous figure because it's the bottom of the envelope.
Yes. Okay. I'm with you. Yep.
Yes, it's the same as we saw on the left panel of previous figure. And all other curves correspond to the temperature inside the star, and the number shows the logarithm of density at each
going in.
Yes, we took this cross section. So 14.5 corresponds to the core. Or everything else corresponds to the crust. And we can see immediately that for the core, the temperature variation is tiny, just a few percent.
Right.
And for the crust, it is much bigger. Basically, the lower the density, the more the more is the variation.
Okay. Very good.
So we can also see that the first extrema, the first minima, exists only for 10 to the 10 grams per cubic centimeter at the boundary. So this is probably some kind of a reaction to a surface boundary condition because it doesn't exist for deeper densities.
Right. Right.
And since it happens at very early times, we should not believe in this peak because TS-TB relation is instantaneous. But in reality, heat takes some time to propagate through the envelope.
Sure.
And for the standard envelope, that is about few months to a year.
Okay.
So everything that happens faster than this time scale, and this first minima happens at just a few weeks.
Few weeks, yeah.
It cannot be trusted.
Okay. So,
but everything, the other extrema, they are more reliable. They correspond to proper time scales.
yeah. This is the cool wave here.
Yes, this extrema corresponds to the heat, to the cold wave propagation from the core to the crust.
Yes. Yes.
And we can see that deeper layers, they thermalize faster. For example, black curve corresponding to 10 to the 14.
Oh, yeah.
Turns back to 1 faster than other curves.
Yes.
And the core even faster than that, because yes, the deeper layers are less affected by rotation.
Okay, cool.
And maybe the last remark, that we have considered also different equation of state for the crust, but the results were virtually identical to the presented here. So there was no point to explicitly plot any figures.
Got it. 97 equations.
So in this paper, we have investigated standard cooling of isolated nucleonic neutron stars, uniformly rotating from frequencies up to the mass shading limit. We specifically investigated the equation of state dependence of thermal evolution.
Yes.
I suppose that we can say our main result is the discovery of the heat blob that forms in the equatorial plane.
Nice. That's this.
And
wow.
yes, this one. And determines the crust thermal relaxation.
Yes. Sure. Very cool. Very cool.
Yes, I guess.
And we have 2 appendices, right?
Yes, well, the first, they're
Just
both slightly technical. The first one describes in more details the concept of heat blanketing envelope.
Okay.
And the second one describes a little bit about the code itself.
Very cool.
How it is written, what solvers it uses, and what test we did to
verify.
To verify the accuracy of the results
correctly. Cool. Very good. Very nice. Mikhail, I want to thank you so much for walking us through this very awesome article on cooling stars, neutron stars in 2D. Very nice.
Well, I want to thank you for inviting me to go through this article.
Sure. You touched on it a little bit as you went through. So let me go ahead and push and ask a little bit. Where do you think we go, let's say, over the next 2 to 5 years on this topic? There's always additional calculations one could run. Do you envision doing this in 3D at some point? Is there some observations, maybe from NICER or some of the other high energy telescopes that could help inform whether we can see these heat blobs and so on? So where do we go over the next couple of years? What do you think?
Well, of course, we can always do more calculations.
Always.
3D would be nice, but probably even 2D with some relaxed restrictions on the flow of matter would be already helpful. Because, like I mentioned, we ignored any non-azimuthal movements of matter, and even to take this into account would be great. Okay. Yeah, as for NICER, they are using some kind of similar models in their calculations. So yes, and they take into account the hot spots on the surface of the star. The trick with the heat blob is that it's inside the star. It is not directly observable. that is the main problem of the heat blob. As was shown on the figures, it is inside.
Do you think there would be some signatures of that from, let's say, R F modes or seismology?
That is an interesting question, because it alters the temperature. Yes, so the temperature becomes dependent on polar angle in the crust. And if we have some temperature-related processes in the crust, that might be possibly observable.
Huh, cool. Okay.
I think that maybe the most promising will be in accreting low mass X-ray binaries.
Ooh, yes.
Because there is a problem of shallow heating that happens somewhere near these densities. Okay, a little bit lower, but still close to the heat blob. And also, these stars can be fast rotators. So it would be interesting to see how the heat blobs affects the evolution of low mass X-ray binaries.
Yeah, cool. Very good.
Yeah, so my next ideas about it is to do the same, but not for isolated neutron stars, but for neutron stars in accreting binaries.
Nice. Very cool. Very cool. Well, I look forward to seeing that come up over the next couple of years. So very good. Very nice. And that will do. So again, Mikhail, thank you very much. And
yes, again, thank you for inviting me.
Sure. Awesome. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Goodbye, everyone.